What is the core objective of federated learning, Florida, mentioned in the paper?
The core objective of federated learning, Florida, mentioned in the paper, is to achieve highly accurate model training without compromising the privacy of client data. Florida is a widely embraced framework for decentralized machine learning model training that aims to allow models to be trained across multiple decentralized edge devices or servers holding local data samples without exchanging them. The paper highlights that recent works have shown that attackers can potentially recover client data by applying reconstruction attacks on the gradient updates sent from the client during training in Florida settings. The privacy concerns associated with Florida are further emphasized, particularly in the context of large language models, LLMs, handling sensitive data within distributed and collaborative learning environments. The paper explores the potential for third-party services or malicious model providers to reconstruct original text from text embeddings, posing a significant privacy risk to users in Florida scenarios.
How does the proposed method embed parrot work in reconstructing the original input text from hidden states? Illustrate step by step.
The proposed method embed parrot works in reconstructing the original input text from hidden states by first selecting a certain layer I from the transformer layers of the attacked model. Then the output embedding of the original input X through layer I is obtained as h_i_x. Embed parrot is trained to generate an output embedding h_i_y that is similar to the initial hidden state h_0_x after passing through the word embedding layer of the attacked model. The training objective is to minimize the difference between h_i_y and h_0_x. Embed parrot consists of three main parts: input adapter, decode model, and output adapter. The input adapter is a linear layer that ensures the hidden size of h_i_y matches the requirements of the decode model. The decode model, which is an only decoder architecture model like GPT-2XL, is used to generate the output embedding. Finally, the output adapter converts the output of the decode model into the hidden size of h_i_y. By combining the restored hidden states with either the HEI or BEI method, embed parrot produces an output that closely resembles the semantics of the original input text. Through training on specific datasets and optimizing for cosine similarity between h_i_y and h_0_x, embed parrot effectively reconstructs the original input text from hidden states, demonstrating its versatility and effectiveness in preserving privacy and security in language models.
What are the datasets utilized in the study, and how are they relevant to the evaluation of the proposed method?
The datasets utilized in the study are the FING PT sentiment, FING PT Fika_Ka, and Wikitext 2 Raw v1 datasets. The FING PT sentiment dataset is designed for sentiment analysis in the financial domain. The FING PT Fika_Ka dataset is tailored for training question answering models in the financial sector, and the Wikitext 2 Raw v1 dataset consists of curated content from Wikipedia. These datasets are relevant to the evaluation of the proposed method as they provide diverse text data for training and testing the embed parrot approach. The FING PT sentiment dataset is used for training embed parrot, while the FING PT Fika_Ka dataset is employed to validate the performance of embed parrot's reconstructed inputs. The Wikitext 2 Raw v1 dataset is utilized to assess the generalizability of embed parrot across different data distributions. By using these datasets, the study ensures a comprehensive evaluation of embed parrot's effectiveness in reconstructing original inputs from hidden states of transformer layers across various text data domains, thereby demonstrating the robustness and versatility of the proposed method in different contexts.
Can you explain the difference in performance of the base embed inversion (BEI) method between CHATGLM6B and Llama 2-7B as discussed in the paper?
The paper discusses the performance of the base embed inversion (BEI) method on CHATGLM6B and Llama 2-7B. The experimental findings reveal that BEI is adept at reconstructing text from the early layers of CHATGLM6B, but its performance diminishes as it goes deeper into the model. On the other hand, for Llama 2 to 7B, BEI's performance for text reconstruction steadily improves with each subsequent layer. The difference in performance can be attributed to the distinct architectural designs of the two models. CHATGLM6B, being an open bilingual language model based on the General Language Model (GLM) framework, may have a different structure that affects the effectiveness of BEI compared to Llama 2 to 7B, which is an auto-regressive language model optimized for dialogue use cases. Additionally, the varying layer depths and attention heads in the two models could also contribute to the divergent trends in BEI performance. Overall, the results underscore the importance of tailoring inversion strategies to suit the specific characteristics of different large language models to achieve optimal performance in text reconstruction tasks.
What are the defense strategies proposed in the paper to protect the privacy of input embeddings?
The defense strategy proposed in the paper to protect the privacy of input embeddings involves utilizing an overlap matrix in conjunction with the discrete cosine transform, DCT, and its inverse, IDCT, to obfuscate sensitive features of the embeddings. The method begins by generating a random permutation of indices from the set 1, 2, L dots, D, and partitioning it into K subsets, each corresponding to a unique overlap matrix O_I in 0, 1 D times D. The overlap matrix is constructed by identifying non-zero indices in each subset, initializing a zero matrix, setting specific values to embed the overlap pattern, and then transposing the matrix to obtain the final overlap matrix. One of the overlap matrices is randomly selected and applied to the input embeddings using the IDCT and DCT transformations. This process disperses the original embedding information across the spectrum and selectively retains or drops information based on the binary pattern in the overlap matrix, thereby altering the characteristics of the input embeddings to impede the recovery of sensitive data while maintaining effective model forwarding. The overlap matrices are saved for repeatability in the transformation process, ensuring consistent application across different phases of model development and evaluation.
What insights are provided regarding the impacts of token length on the performance of embed parrot in text reconstruction?
The paper provides insights into the impact of token length on the performance of embed parrot in text reconstruction. Specifically, the study reveals that for CHATGLM6B, embed parrot shows poorer performance in reconstructing shorter texts compared to longer ones. This is attributed to CHATGLM6B's utilization of the GLM architecture, which captures hidden relationships between tokens more effectively in longer sequences, leading to richer semantic information that aids in reconstruction. On the other hand, for Llama 2 to 7B, the impact of token length is relatively minimal, with consistent performance across various token lengths. Although there is a slight decline in Rouge and F1 scores within certain token length intervals, the sentence BERT semantic scores remain stable. This suggests that while the accuracy of tokens reconstructed by embed parrot may vary, they tend to maintain a high degree of semantic similarity, even if not exact replicas.